So a review before we start doing problems. If we have a statically, break. 2, 1. So before we start doing problems, let's just review how we're going to solve them for a statically determinate beam. Right? That's one that has the same number of external support forces as it does linearly independent equations of equilibrium. If the beam is determinate, then we're going to be able to solve, and we are going to be required to solve for m of x by statics, and it will be a function of only the applied external loads. Depending on how the supports are arranged, we may have to do some work before we're able to use the blue saw and cut the beam open. Again, just depends on where the support forces are located. There's our second order beam equation relating the curvature of the beam to the moment, and then the material property E and the cross-sectional property I. So there's our starting point to integrate. Now, as we integrate, we're going to have to introduce boundary conditions. For a determinate beam in 2 dimensions, we're going to have 2 physical boundary conditions. That means we're either going to have a slope and a displacement that's known on the beam, or we could possibly have 2 known displacements. And as we integrate, we apply them where appropriate, and we end up in the end with an expression for v of x. This will be a function. It'll be based on the location x, we'll be able to find the transverse deflection. Here it is graphically. There's the moment. We cross over from the internal force world to the physical world, the curvature world, and we integrate down to the displacement v. We can then go the other way using differentiation. If we wanted to do it by 4th order beam, so we can avoid solving for the m of x inside the beam, but at the expense of doing more integration. So what we define functionally is the applied external load, the distributed load on the beam. We're going to have 2 force boundary conditions and 2 physical boundary conditions. So these again are based on the blues, so either displacement or slope. The forces are going to be moments or shears that are known along the location of the beam. And we would integrate this 4 times and apply these 4 boundary conditions when appropriate. Solve for v of x. From that function of displacement as a function of x, we can use differentiation to go head back and get some other equations for slope. We could get the equation for moment, right? By differentiating twice. You do it one more time, you're going to end up with the equation for shear. For an indeterminate beam, we're going to focus on something that is 1 degree indeterminate. And so we are going to determine m of x because we need m of x to be put into the 2nd order beam equation down here. But because the beam is indeterminate, by statics, we're going to find m of x, but it's going to be a function of an external support force. And with the color culture that we have, we're dealing with a, quote, red arrow, something that is an external support force. So we are going to have an additional unknown in our formulation because as we integrate this twice, we are introduced to 2 constants of integration. So as we look at our beam, we're going to find that it is going to have 3 physical boundary conditions. Those 3 physical boundary conditions are going to need to be applied as we integrate, and then we would end up with an expression for v of x at the end. Right? There's 3 physical boundary conditions because the beam is over-restrained. Sometimes it's referred to. Same idea graphically, m of x. We're going to end up down here at v of x. It's just that we have more unknowns, which is fine because we have more boundary conditions. We have more constraints, more kinematic restraints on our beam. If we wanted to do it by 4th order beam equation, going to define W of x, the distributed load on the beam. For a 1 degree indeterminate, our 3 physical boundary conditions are going to be mixed with only a single force boundary condition. And in the end, we're only going to have 4 boundary conditions. For a determinate beam, it was 2 physical and 2 force. For a 1 degree indeterminate, it's going to be 3 physical and 1 force. Exact same procedure. Integrate 4 times. Apply the 4 boundary conditions where appropriate. And you'll have v of x.